Well, in the last couple of videos, we talked about vertical asymptotes and infinite limits at a point. But now we're going to talk about limits at infinity and horizontal asymptotes. So you'll notice this function here, which we'll call f, has the property that as we go further and further to the right, it's the output values are getting closer and closer to 4. So if we plug in 5, we get something a little bigger than 4. If we plug in 10, if we plug in 20, we go further and further out. The values are getting closer and closer to 4. Notice we have this horizontal asymptote at a height of 4. And what we say is that this function has a limit of 4 at infinity, or the limit as x approaches infinity of f of x is 4. Okay, now the function also has the property that as we move further and further to the left, so if we plug in -5, -10, -20, the outputs are going to get closer and closer to -2. So we say the limit at negative infinity is -2, or the limit as x approaches negative infinity of f of x is -2. And you'll notice here we have these horizontal asymptotes. Y equals -2 and y, well, that's supposed to say y equals 4. Y equals -2 and y equals 4 are the horizontal asymptotes of this function. And by the way, we always use y equals when we're talking about horizontal asymptotes because the equation of a horizontal line is always y equals a number, just like the equation of a vertical line is always x equals a number. So we have these two horizontal asymptotes, y equals -2 and y equals 4 for this particular function. And what happens to the function as we go further and further to the right or further and further to the left is sometimes called the end behavior of the function. So the right end behavior has to do with what happens to the function as we move further and further to the right, as we approach positive infinity. The left end behavior has to do with what happens as we approach negative infinity, as we go further and further to the left. By the way, one thing I should mention is we never talk about left and right hand limits at infinity. You can't approach infinity from the left or from the right. I guess in some sense, when you're approaching positive infinity, you're kind of always approaching from the left, but we don't think about it that way. So we just talk about limits at infinity or at negative infinity. Now we can also talk about infinite limits at infinity. So this happens with a lot of just normal functions. For example, like y equals x squared or f of x equals x squared looks like this. As we go further and further to the right, the outputs aren't getting closer and closer to some number, like having some horizontal asymptote. The outputs are actually blowing up. So as we go further and further to the right, it blows up to infinity. We say the limit at infinity is infinity. Okay, this has an infinite limit at infinity. Okay, now as we go further and further to the left, okay, as we approach negative infinity, the outputs are also approaching positive infinity for this function. So we say this function has an infinite limit, or a limit of positive infinity, at negative infinity. Okay, now we also have a theorem that's similar to a previous theorem that we had. Remember the theorem that we had that said the limit of the sum is the sum of the limits? Well, the same thing can be said for limits at infinity. So suppose the limit as x approaches infinity of f of x and the limit as x approaches infinity of g of x both exist. And in particular, they're not plus infinity or minus infinity, they're just numbers. Then all the corresponding conclusions of our previous theorem on limit computations also hold. So the limit of the sum is the sum of the limits, or the limit of the product is the product of the limits. And the same thing also holds for limits as x approaches negative infinity. Okay, so as a quick example, if the limit as x approaches infinity of f of x is 6, and the limit as x approaches infinity of g of x is 2, what's the limit as x approaches infinity of f of x minus g of x? Well, it's going to be 6 minus 2, okay, which is 4. Okay, now the question is, how do we find the limit as x approaches infinity if we're given a formula for a function? So we'll begin with a polynomial. Now, it turns out that with polynomials, what really matters as far as the end behavior goes, so the limit as x approaches infinity or negative infinity, is the leading term. In fact, that really comes from the leading term test from algebra. So if we plug in a really big positive value for x, let's say like 100, well, 8 times 100 will be kind of big, 800, and 100 squared is big. It's 10,000 times 70 would be 7,000, 70,000. But 100 cubed is way bigger. Okay, it's a million. So, and if you plug in 1,000 or a million or a billion, the x cubed is really going to overpower these terms. So when we take the limit as x approaches infinity, these other terms aren't even going to matter. Okay, now these other two terms do matter if we're saying limit as x approaches 5 of something, or limit as x approaches 2 of something. But when we're looking at the end behavior, limit as x approaches infinity, the only term that really matters is the leading term, the term that has highest degree. It's not always the term that appears first in the equation, but the leading term is the term that has highest degree. So now, what is the limit as x approaches infinity of this? Well, we could look at the graph of this function, but one way to think about it is what if we plugged in a really big positive number for x, like 10 or 100 or 1,000, and suppose we plug in that number, like 10 or 100 or 1,000, and we cube it. What kind of number do we get? Well, we get a really big positive number. So our answer is positive infinity, or just infinity, you could write. Now, what if we approach negative infinity? What if we plug in a really big negative number, like negative 10, let's say? Well, negative 10 cubed is going to be a negative number, right? Negative 10 times negative 10 times 10. It'll be a really big negative number. And then these numbers are going to be much smaller, so they're not really going to affect the answer. So our answer in that case would be negative infinity. So limit as x approaches negative infinity of this would be negative infinity. So the leading term test from algebra essentially says that the end behavior of a polynomial matches the end behavior of its leading term, the term with highest degree. So if you remember, polynomials really come in 4 flavors. If you look at the graph of a polynomial, it'll either look something like this, or like this, okay, or like this, or like this. Okay, so if you have an even degree polynomial, it's either going to look like this one or like this one. Either both arrows will kind of be facing up. The graph might wiggle around some in the middle, but on the end, both arrows are either facing up or facing down. So that's if you have an even degree polynomial. Now, which one is it? Well, if you have an even degree polynomial with a positive leading coefficient, the graph looks like this. If you have an even degree polynomial with a negative leading coefficient, the graph looks like this. Now, odd degree, by the way, prototypical examples of this would be like x squared would be a prototypical example of this, right? Notice x squared just looks like this, right? Okay, it doesn't wiggle around at all. It just looks like that. A prototypical example of an even degree polynomial with a negative leading coefficient would be like negative x squared, which looks like this. Okay, again, it doesn't wiggle around, but it has that shape. Now, for odd degree polynomials, they either look like this or like this. If it's an odd degree polynomial with a positive leading coefficient, like x cubed, the graph has this basic shape. Again, x cubed doesn't wiggle around at all like some polynomials do. But that's what the basic shape is. If it's an odd degree polynomial with a negative leading coefficient, like negative x cubed, the graph will look like this. Remember, x cubed looks like this. Negative x cubed looks like this. Okay, so what really matters is the leading term. So let's do a few examples here. If we're looking at these polynomials, we want to know what is the end behavior of these polynomials. Well, let's look, for example, at, notice, by the way, a and b are the same function. We're just approaching infinity or negative infinity. And c and d are the same function. We're just approaching infinity or negative infinity. So let's pick one of these. Let's pick like, let's say d. Okay, and let's try to figure out what's the limit as x approaches negative infinity of this function. Well, let's pick out, first of all, the leading term. The leading term is this. It's the term with highest degree. So we can kind of ignore these other ones. What's the limit as x approaches negative infinity of this? Well, one way to think about it would be in terms of its graph. What does the graph look like? Notice it's an even degree, so both arrows should be facing the same direction, either both up or both down. But it has a negative leading coefficient, so both arrows should be facing down. So the graph is going to look something like this. Okay, well, notice as we approach negative infinity, as we go further and further to the left, the function is going down, right? So as we approach negative infinity, this would be negative infinity. By the way, as we approach positive infinity, it's also going down, right? So that would be negative infinity. So even degree polynomials kind of have the same end behavior as you go to the right or to the left, right? Notice the leading term test, that's what it says. Odd degree polynomials have kind of opposite end behavior depending on whether you're going to the left or to the right. So I'll let you try pick one of these examples here. So I picked D here at C and D, but pick one of these examples and try the problem. I'll give you a few seconds to do this. Here are the solutions. Now notice, let's just pick one of them and look at it. Notice, for example, on part H here, what's the limit as x approaches negative infinity of negative x to the 7th plus 5x plus 29? Well, again, the leading term is what really matters. We have a negative coefficient with an odd degree, so the basic shape of the graph is going to look something like this. Right? So as we approach negative infinity, as we go further and further to the left, the graph's actually going up to positive infinity. Now, as we go to positive infinity, it's going down to negative infinity. So one way to think about it is in terms of the graph. The other way to think about it, though, is what if you plugged in a really big negative number, like negative 100 for x? Everywhere you see an x here. Well, these other terms, we can kind of ignore these terms here. But if you plugged in like negative 100, if you raised negative 100 to the 7th, you would get a negative result, a huge negative number. But then if you put this negative in front of it, it becomes positive again. So that's why we're approaching positive infinity. Okay, now what about rational functions? So what about if we have a function like this? What's the limit as x approaches infinity of 8x plus 3 over 2x plus 1? Now imagine plugging in a really big positive number, let's say like 100. What if you plugged in 100 for x? What kind of number would you get? Well, if you plugged in 100 here, 8 times 100 would be 800 plus 3. That'd be 803. In the denominator, we get 201. Okay, so if we plugged in 100, we get 803 divided by 201. Well, if you do that on a calculator, that's really close to 4. Okay, that's really close to 4. In fact, let me open up Desmos here. I actually plugged in 10 here, and notice I got 3.9528. Okay, if you plug in 100 in both places, I get 3.995. If I plug in 1,000, I get 3.9995, right? I'm getting numbers that are really close to 4. Okay, so what's happening here? Well, notice as the x values get bigger and bigger and bigger, outputs are getting closer and closer to 4. Essentially, what's happening is that the 3 and the 1 don't really matter so much. What really matters is the 8x over the 2x. Again, the leading term up here and the leading term down there. And if you do 8x divided by 2x, you just get 4, right? So notice, by the way, on the graph of this function, this has a horizontal asymptote at a height of 4. As we approach infinity, the output values are going to get closer and closer to 4. By the way, as we approach negative infinity, if we're to plug in negative 1,000 in both of these, notice we're getting outputs, in this case, are slightly bigger than 4, but it get closer and closer to 4. Okay, now looking at this right here, how could you figure out that the answer was going to be 4 without knowing the graph or without plugging in numbers? Well, the easy way to do this, let me tell you the easy way first of all. If you have a rational function, so it's a polynomial divided by a polynomial, if the degree of the polynomial up here is the same as the degree of the polynomial down there, you just have to look at the leading coefficients. In this case, it's 8 and 2. Divide those out, and that'll be your answer. Okay, so in other words, the answer is just going to be 4. Right? And y equals 4 would be a horizontal asymptote of this. Okay, now this example here, notice we have a rational function. The degree is 4 up here, the degree is 4 down there. So they have the same degree. So again, we look at the leading coefficients. The leading coefficient is 18. The leading coefficient there is negative 3. 18 divided by negative 3 is negative 6. Okay, you're going to have a horizontal asymptote of y equals negative 6. Okay, now again, that's the quick way to do it. If you actually wanted to look at it kind of the long way, how would you do this? Well, the way to figure this out with the theorems is, first of all, can you do limit of the quotient equals quotient of the limit? So would I be allowed to do limit as x approaches infinity of 8x plus 3 divided by limit as x approaches infinity of 2x plus 1? Okay, would I be allowed to do that? Well, you can do limit of the quotient as quotient of limits as long as you're not dividing by 0, but that's exactly the case we're in, or as long as we have these limits exist and we're not dividing by 0. But notice these limits don't exist. The limit as x approaches infinity of this is infinity. And this limit is also infinity. So we get infinity over infinity, and that's a problem, just like a 0 over 0. So we actually can't do limit of the quotient as quotient of limits because we get these infinite limits. So actually, what do you do in this case? Well, in this case, if you wanted to figure out the hard way, what you would do is multiply the numerator and denominator both by 1 over x. Okay, in this one down here, you'd multiply the numerator and denominator by 1 over x to the 4th power. Okay, because the highest degree power highest power that occurs is x to the 4th. But in this one, you multiply by this. So then you'd write limit as x approaches infinity of, well, if we distribute the 1 over x, 8x times 1 over x is just 8. 3 times 1 over x is just 3 over x. And then down here, we'd have 2 over x, or 2x times 1 over x would be 2. And then we do 1 times 1 over x is this. Now, at this stage, we could do limit of the quotient is quotient of limits because this top limit is going to exist. Because as x approaches infinity, this one is going to approach 0. And as x approaches infinity, this one will approach 0, right? If you plug in bigger and bigger values for x, 3 over 100, 3 over 1,000, 3 over a million, that's going to approach 0. Same thing here. This one will approach 0. So we can do limit of the quotient is quotient of limits, and then the top limit of the sum is the sum of the limits, and so forth. The point is, in the top, you're going to get 8. In the bottom, you're going to get 2. Just like we thought. We get 4 as an answer. So again, that's the long way of doing it. You could do the same thing here. You multiply each term by 1 over x to the 4th. These terms are going to approach 0, the lower degree ones. This one will actually approach 18. This one will approach negative 3. Your answer is going to end up being 18 over negative 3, which is negative 6. Okay, that's the long way. If you try to look at My Math Lab and say, help me solve this or view an example, it probably shows you this long way. But if the degree is the same on the top as the bottom, it's really easy. Just look at those leading coefficients. Okay, 8 over 2. Okay, 4. So the horizontal asymptote here would be y equals 4. Horizontal asymptote would be y equals -6 there. Okay. Now, what about these examples right here? Well, what if we have the degree on the bottom is bigger than the degree on the top? So we have an x to the 5th power down here, and we only have a 7x squared up there. Well, if you wanted to do it the long way, you'd have to multiply the top and bottom by 1 over x squared, okay, the smaller of the two. But the quick way to do this is the answer is actually just going to be 0. Okay, because if you plug in a big positive number for x, so plug in like 10, well, 10 to the 5th power is just astronomically large, whereas 10 squared is only kind of big. Okay, so what you're going to get if you plug in a really big positive number, the denominator is going to be huge compared to the numerator. And so, in other words, the fraction is going to be lopsided toward the denominator. So, if you take a kind of big number divided by an astronomically large number, then you're going to get something close to 0. In fact, I graphed this on Desmos. And you can see, notice, there's the function here. What happens as we approach infinity? The output values are getting closer and closer to 0. Okay, and same thing as we approach negative infinity, by the way. The output values are going to get closer and closer to 0. So what that really means is y equals 0, which is really the x-axis, is a horizontal asymptote. So whenever the degree on the bottom is bigger than the degree on the top, you'll always get the x-axis, or y equals 0, to be your horizontal asymptote. Okay, remember, if the degree is the same on the top and bottom, you look at the leading coefficients. If the degree on the bottom is bigger than the top, you get 0. And so y equals 0, or the x-axis, is the horizontal asymptote. Now, what about if the degree on the top is bigger than the degree on the bottom? Well, in this case, again, you're going to actually end up getting either positive infinity or negative infinity as your answer. How do you determine which? Well, one way to think about this, if you plug in a really big number, so we're approaching negative infinity, so maybe plug in a big negative number, like negative 100. Well, the top part's going to be a huge, huge number. It might be a huge negative number or positive number. You have to figure it out. The bottom number will be a kind of big number, but a fraction that is lopsided toward the top, that has a number that's way bigger on the top than the bottom, will have a very big result. So we're going to get a very big result, but we don't know whether it's positive infinity or negative infinity. So again, if the degree on the bottom is bigger than the top, y equals 0 is the horizontal asymptote, so the limit is 0. If the degree on the top is bigger than the bottom, it's either going to be plus infinity or minus infinity. How do we figure it out? Well, again, just ignore the lower degree terms and just write it as minus 5x to the 6th over 31x cubed. Now, again, we can only ignore these because we're approaching infinity. If we were taking the limit as x approaches 2, you definitely can't ignore these. The limit as x approaches infinity or negative infinity, you can ignore those. Well, now notice what happens. This is the limit as x approaches negative infinity. We can write this coefficient out front here, negative 5 31st. And then notice we have x to the 6th over x cubed. That's really just x cubed. So now notice we just have a polynomial here. What happens as we approach negative infinity? If we plugged in a really big negative number, let's say negative 10, let's say, negative 10 cubed is a big negative number, right? It'd be negative 1,000. But when you multiply it by a negative number, it's going to be positive. So this is going to be positive infinity. Okay, if we had approached positive infinity, took the limit as x approaches positive infinity, we plug in a big positive number. If we cube it, we get a big positive number. And then we multiply it by negative, it will be negative infinity. So that's how you look at the end behavior of rational functions. So again, there's 3 cases. If you have p of x over q of x, you have 3 cases. If the degree of the top is the same as the degree of the bottom, you just look at those leading coefficients and divide them out. You're going to get like y equals 4. Something like that as a horizontal asymptote. The limit will be 4. If the degree on the top is less than the degree on the bottom, right? The degree on the bottom is bigger, y equals 0 will be the horizontal asymptote. And if the degree on the top is bigger, the degree of p is bigger than the degree of q, then you're going to get either infinity or negative infinity. You have to figure it out which one it's going to be.